Hi, everybody. I'm Sydney. I'm a semester and a few months into my master's research. I work with Dr. Mindy Morales-Williams, and today I'm going to tell you about my research thus far and really a lot. So hope you're all ready. So I look at, so I'll tell you what I'm talking about. My project is related to assessing the sensitivity of acid-impaired lakes to increase algal productivity in Vermont. So just a little bit of background before we jump in. Acidification is a regional problem. So look at acid rain and how that affects lakes in the state. What is acid rain and where does it come from? The short explanation is acid rain is sulfur dioxide and nitrogen oxide formed with water molecules, oxygen, and other chemical compounds in our atmosphere. And then from there you get sulfuric acid and nitric acid, and then that bonds with water molecules, and we have acid rain. This is by no means just a regional problem that Vermont is dealing with. This is more global. And so many lakes in Vermont and the northern hemisphere, there's been studies done in Ontario and also in Sweden that have been impaired by acid rain deposition. And lakes are a really good sentinel of large-scale and regional-scale global change, and that's because they respond to these different influences such as acid rain, and we can see what's going on in these systems. So reductions in acid rain deposition, that's a good thing. Yes, it's a good thing. These lakes are showing positive rates of recovery, and those rates of recovery are appearing as increases of pH, and also the recovery of aquatic species. We're seeing more productivity in these lakes, which is also really great. However, it's not all good news that we think. As these lakes recover, their ecology is changing rapidly, and that's really intriguing for a handful of reasons. And additionally, some of these lakes are turning brown, and other lakes are becoming more productive. Now, what's interesting about these lakes that are turning brown is historically they haven't been this dark in color. And so with a decrease of sulfur deposition from the atmosphere, there's an increase of temperatures of soil and also an increase in precipitation that's resulted in the transport of soil microbes from the terrestrial environment into the aquatic environment. Other lakes are becoming more productive that have been historically low nutrient and not as productive, and that's because as they recover, these bodies of water are becoming more alkaline, and that's more amenable to different phytoplankton growth, and these community dynamics are becoming much more interesting. So my research focuses on two large questions, but this evening I'm just going to talk about the one that's bolded on the top. So are lakes recovering from acidification at risk of increased harmful algal blooms? And how do these differ between the lakes that are clear in color and the lakes that are more brown? So you hypothesize that phytoplankton productivity will be measurably lower in lakes that are more brown and recovering from acidification than the clear lakes. And this could be due to light limitation. So my research, I have a kind of a three-component aspect to what I'm looking at. I'm using long-term data, I'm using modern ecology, and also a multi-proxy paleolimnological approach, which is a total mouthful to say. And paleolimnology is basically the reconstruction of past environments. So I took a sediment core from a lake, and in the sediment core are these diatoms. And not only do they look really cool, they are really cool. So diatoms are unicellular phytoplankton, and they have a glass-like cell wall. So when they are happy and alive in the water column, so they are happy and alive, then they die. So they sink to the bottom of the lake, and they preserve really well in lake sediments. They're really important because they're super sensitive to all these environmental changes. So each diatom, there's about 10,000 species that are known, but each diatom has different tolerances to pH, to nutrients, climatic change. So, for example, this guy, the Brachythyropoid, they love low pH water. And so, from the sediment core, I took it from the middle of the lake at the deepest part of the lake. I'm expecting to see a whole bunch of Brachythyropoids at the bottom of that sediment core. But as we move up the core, little dinner plate looking diatoms like that one, they prefer more alkaline waters. So I'm expecting to see those communities of diatoms appear more up there. I currently have the pleasure of working with Rebecca Harvey from the DEC, and 12 lakes that are in the state of Vermont. The bulk of them are in the south of Vermont. One's in the middle, and then the sediment core that I've been talking about is all the way basically in Canada, Beaver Pond up there. So 30 lakes have been identified by the DEC as acid impaired. Of those 30 lakes, 12 are a part of the DEC's long-term monitoring of acid-sensitive lakes program. These lakes there's a handful of them that are higher in dissolved organic carbon, so they're more brown. There's a handful that are lower in dissolved organic carbon, so presented more clear. And I should mention that these lakes that are turning brown, it doesn't necessarily mean it's bad. So think of a brown lake like you think of a cup of tea. You boil water, you put your tea bag in, your tea water turns more brown. The same thing's happening to these lakes. So in addition to being able to collect all my samples, so just to clarify, there's one sediment core. If I were counting 12 sediment cores, that'd be here for more than 2 years. But the phytoplankton samples are coming from all the lakes down here. And I'm biased, but I think my research is really awesome because sometimes I commute to work in a blow-up raft. And all these lakes are pretty much hike-to locations. So we pack up our bags, put our raft in our bag, and then get to these lakes, sample, and have to pack everything out. So a lot of the anthropogenic inputs that we're seeing are atmospheric. So they're not near roads, they're not near ag land. So it's a lot of environmental factors that we're weighing here as the lakes are responding to, or as lakes are recovering. So I'll do a quick information on my method. So I mentioned earlier that I'm using long-term data. So these lakes, every time they're monitored, there's a whole suite of parameters that are entered into this database called the Vermont Integrated Watershed Information System. This has become my best friend in the past couple months because I'm able to pull temperature data, dissolved oxygen, dissolved organic carbon, pH, and with those you can track changes in the lake's chemistry. And that's been really valuable as we keep change happening. And so my multi-proxy paleolimnological approach, this is how I get my diatoms from the bottom of the lake to under the microscope. So the sediment cores are extracted, and then we subsection at every 2 centimeters. And sometimes it's a smaller increment, but for the purpose of this, I'm just looking for the shift in these lake diatom communities. So we clean dirt in the lab, so to get our glass-like, or diatoms, which have their glass-like cell walls. And then each slide is then analyzed, and 300 valves are identified at a minimum, and then all those data are compiled, and that allows us to see the shifts of these diatom communities, and from there we can draw conclusions of what's happening in these past climates. So some preliminary results. I have an elemental analysis that was done from the sediment core, and just to orient you, the depth is centimeters, but this is the top of the core, and we're working our way down. The blue bars you can see are the obvious shifts that we've seen, and we're speculating at this point that that's the shift down here is when deforestation in Vermont was occurring. So we're seeing a increased transport of sediments from the land to the water. So we lost our buffer, and the sediment core will be dated. So we'll be able to precisely identify the different events or where the shifts are occurring by dates. And this lead to 10 dating process will hopefully get us about 150 to 200 years back in time. And then we've also seen increases in pH in a handful of these ponds. These 4 in particular have reported about 1 unit of pH over time. I should mention that all these averages are annual averages. So we're excited to see these 4 ponds are a mix of, for example, Beaver Pond is a lower DOC pond and Big Mud is a high DOC pond. So we're interested to see how those ponds continue to respond and recover from acidification. So some next steps, like I said, the sediment core will be sent off and be dated. I'll continue my sediment diatom identification and analysis. And the really exciting part is I get to move on to phase 2 of this project, which is modern ecology. My samples have already been collected and they're patiently waiting to be analyzed. But by analyzing modern algal community dynamics, I'll be able to see what's occurring in these lakes now, and that will allow us to hopefully predict what could happen as we move forward. So just to summarize, really fast summary. Recovery is happening, and I think there's a huge benefit to collecting both modern ecological data and paleolimnological data, because that will provide a huge timescale of what's going on in these systems. The paleo aspect gives us a regional idea as to what's going on, and the modern ecology tells us what's going on today, and that can allow us to possibly predict the severity and frequency of these blooms as we move forward. So that's the missing piece of the puzzle. And really quickly, I'd like to thank my advisors, Mindy, for your support, and my committee members, and Rebecca Harvey, Heather Pembroke, and Kelly Morrow from the DUC for letting me be a part of the project. Thanks. Like a sprint. Yes.
Do you expect pH to continue to recover, or sort of stable, or perhaps could it progress as the lake functions as more of a carbon sink?
Yes, to both. We hope to see recovery, and then lakes will kind of recalibrate at a certain level. But also, the other side of your question, if carbon or if CO2 rates continue to increase in lakes, it could become more acidic. Hopefully, we don't get to that point, as these lakes haven't historically been like hyper-eutrophic or eutrophic even.
Excellent. Thank you so much. Good job.